Okay, for open addressing, I'm going to represent the underlying array with these little egg cartons, and I've labeled the indices 0 to 9. Unlike chaining, in open addressing, each index is only ever going to store one element. That's really important. Open addressing, each index is only ever going to store one element. So to represent that, I'll write the strings on a little piece of paper inside one of these plastic capsules. So open addressing is going to be different in that we only store one element at each index. And the really important other thing that you'll notice is that we're going to handle it differently when we find an empty array index. And we'll talk through that. Okay, we're going to be working with the same code. And I just added one line. I'm checking for contains camel a second time. Okay, let's run through it. So again, this is a hash set that's holding strings for us. And you're going to imagine that I am the hash set, so I'm executing this. On our first line where we want to add tiger, remember, again, we need a repeatable way to figure out where we would put it. So we're going to call hashcode on tiger. Hashcode on tiger returned that number over there. And we're going to, again, use the last digit because we have 10 array elements. We're going to use the last digit to determine which array index to put it at. So the last digit is a 7. So I'll go to index 7. I'll find that it's empty. And so I'll put tiger at index 7. Okay, my next line to check if if my set contains tiger. Again, I need a reliable way to know where to look for it or where I would have put it. So I'm going to call hashcode on tiger. Hashcode on tiger is going to return that number there, 80, 80, 60, 47. I have decided to use the scheme where I use the last digit, so that's 7, to look for it at that index. So I'm going to go to index 7, and I find it's not empty. So what I'm going to do is I'm going to call dot equals with tiger that I'm trying to check for and the tiger that's already at that spot. I find that they are dot equals, so contains returns true. All right, next up, I'm going to add panda. I need a reliable way to know where I would have put it, so I'm going to call hashcode. Hashcode returns the value shown there. That last digit is a 4, so I'm going to look at index 4. I find that index 4 is empty, and so I can add panda there. My next line, I'm going to try and add panda again. Remember, we're working with a set, so we're not going to keep duplicates. So I need a reliable way to know where I would have put it or where I should put it. And so I'm going to call hashcode on panda. And then I decided on the scheme to use the last digit, but I can use anything as long as it's consistent. The hashcode of panda returns that number. I'm going to use that last digit, which is 4. So I'm going to look at index 4. I find that it's not empty. So what I'm going to do is I'm going to compare panda that I'm trying to add with the panda that I already add using dot equals. And those are dot equals. So I don't need to add another copy of it. Okay, next up I want to add zebra. I need a reliable way to know where to put it, so I'm going to call hashcode. Hashcode returns the number there. I'm going to use the last digit, which is a 0. I look at index 0 and I find there's nothing there, so I'm able to add zebra. And you might have noticed that I'm trying to use colors in a consistent way throughout this. Any element with the same last digit in their hash code will have the same color. Okay, I've added zebra. Let's go on to giraffe. So I want to add giraffe, so I need a consistent way to know where I want to put it. So I'm going to call hashcode on giraffe. Hashcode on giraffe gives me the number there. Its last digit is a 2, so I'm going to look at index 2. I find that index 2 is empty, so I'm able to add giraffe. Okay, next up I want to add bear. So I'll call hashcode on bear. I get the value there. The last digit is 8, so I look at index 8. I find it's empty, and so I can add bear. Next up, I want to add lion. I need a reliable way to know where to put it, so I'm going to call hashcode. When I call hashcode, I get that number there. The last digit is a 2, so I'm going to go to index 2. Okay, but index 2 isn't empty, so I need to call dot equals with the lion that I'm trying to add and the giraffe that I find at index 2. They are not dot equals. I still want to store lion, but I've decided that every array index is only ever going to hold one item. So I need to find an open array index where I can put lion. I can't put it at index 2, so I'm going to try one ahead and try and put it at index 3. I find that index 3 is empty, and so I'm going to put lion there. Okay, next up I'm going to try and add camel. I want a reliable way to figure out where to put it, so I'm going to call hashcode. Hashcode returns the number there. Again, the last digit is a 2, so I'm going to look at index 2. I find index 2 is not empty, so I compare the camel that I'm trying to add with the giraffe that's in index 2. They are not dot equals, but I still need to find a place to put camel. So I'm going to go from index 2, which is full, and check index 3 to see if it's empty. Index 3 is not empty. But remember, I need to double check that camel's not already in here. So I'm going to compare the camel that I'm trying to add with what I find at index 3, which is lion. Those are not dot equals, but I still haven't found where I can put camel. I tried index 2, now I tried index 3. Next, I'm going to try index 4. I look at index 4, and index 4 is also not empty. So I need to compare the camel that I'm trying to add to what I find at index 4, which is panda. They are not dot equals. So again, I need to keep going. I've tried index 2, I've tried index 3, I've tried index 4, now I need to try index 5. When I get to index 5, I find that it's empty, and I can add camel at index 5. Okay, we'll get to see some of those same steps repeated when we look for camel using contains on the next line. So let's do that. Okay, I want to check if my hash set contains the string camel. I need a reliable way to know where I would have put it. So I'm going to call hashcode on camel. Hashcode on camel returns the number there. I'm going to use the last digit, which is a 2. So I'll start by looking for it at that array index. I look at index 2 and it is not empty. And so I can't compare the camel that I'm trying to add to the thing I find at index 2, which is giraffe. They're not dot equals. And so I need to go to the next index, which would be the next place I would try and put it. So now I've checked index 2, I need to check index 3. At index 3, I find it's not empty, so I need to compare the camel that I'm checking for with the thing I find at index 3, which is lion. I use dot equals and I find that they are not dot equals. Now that I've checked index 3, I need to check index 4. I want to see if index 4 contains camel, so I'm going to compare the camel that I'm trying to check for with the panda that I find at index 4. They are not dot equals, so I'm going to go on to index 5. At index 5, I find it's not empty, so I need to compare the camel that I'm trying to check for with the thing I find at index 5, which is camel. Okay, they are dot equals, so I'm able to return that yes, my set contains camel. Okay, next up I want to remove lion. Remove, contains, and add, they all use the same basic algorithm to figure out where I should look for that element. So I'm going to call hashcode on lion. Hashcode on lion returns the number there. The last digit is a 2. That's the digit I'm going to be using to figure out where to look. So I go to index 2. I find it's not empty. So then I need to compare the lion that I'm trying to remove with giraffe that I find there. They're not dot equals. So I'm going to go to index 3. I find index 3 is not empty. So I'm going to compare the lion that I'm trying to remove with actually the lion that I find at index 3. So I found the thing I want to remove. Here's where I think it gets really interesting. Can you imagine that if I just remove that lion, I would no longer be able to find camel? Because if somebody was looking for camel, they would check index 2, not find it, then get to index 3, find that it's empty, and assume that camel wasn't in there. So I need to do something trickier than just remove lion outright. And what we call this is we're going to put a gravestone in. So I'll represent that as a little RIP. And that's going to help me remember there used to be something here. We can look at how that will work trying to look for camel. Okay, so the next line is my set.contains camel. So I'm going to look to see if my set has camel in it. I need a repeatable way, so I'm going to call hashcode. That's going to give me that number there. I'm going to use the last digit, which is a 2, so I'm going to go to index 2. I find that index 2 is not empty, so I'm going to compare the camel that I'm looking for with the giraffe that I find there. Those are not dot equals, so I'm going to go to the next index, index 3. At index 3, I find it's not empty, but it's an RIP. It's one of those gravestones. So I know both that this is not my item and I need to keep looking. So I'm going to go to index 4. At index 4, I find it's not empty. And so I compare the camel that I'm looking for with the panda that I find at index 4. Those are not dot equals. So I need to go to the next element. That's index 5. And I'm going to compare the camel that I'm looking for with the string camel that I find at index 5. Those are dot equals, so contains can return true. And you can imagine if index 5 had been empty, I would have checked giraffe and the spot with the RIP, that gravestone, and the spot with panda. And so if I got to index 5 and it was empty, I would know that camel wasn't in there. Okay, so with chaining, we could hold multiple things at a single array index. But here we only have a single item at each array index, which means when we have a collision, so two things should be put at the same spot, I need a strategy for finding a new place to put it. Here I just went one index ahead. You could do more complicated things like, oh, instead of doing one index ahead, do it 3 index ahead, and then 3 indexes ahead, and then 3 indexes ahead. But that variation isn't super important for us right now. So if I found that the spot I was looking in was full, I would go 1 index ahead and look for it there. Still full, 1 index ahead until I found an empty spot in my array. And to make all that work, it makes a remove a little bit trickier where I can't just remove it. I have to use this gravestone as a placeholder so I can still find things even if they're not at the index where they initially should be, because they might end up a few indices away.